this podcast, Brett from Akamai talks about forecasting and his world as a chief data strategist. Stay tuned. Welcome everyone to another episode of Future of Data podcast. Today we have with us a very special guest. So we have Brett McLaughlin from Akamai, and he's a chief data strategist. So he is the first chief data strategist that we are talking to, and I'm super excited and pumped to have a conversation with him. Brett, welcome to our podcast, and thank you for accepting our invite.
Of course, I'm excited to be here.
Beautiful. So I think as a start, I would love to know your background. And I did some research, but I think you have a very fabulous and very vibrant background. Why don't you walk our guests through your journey of how you are here, where you are here, and what was your background? That would be really, really amazing.
Oh, sure. Yeah. So, my background started very differently from most of the proper, say, data scientists that you'll see. And that my background was really in reporting. I started my career. I graduated from Emory University in 1995, and immediately jumped into what was then the hot new field of data warehousing. And so that was really this idea that companies were starting to realize that. One, they had access to a lot of data because they were starting to digitize more and more. And then two, that the data wasn't really in a format that really let them easily report on it. And so around that time, there was this whole concept of saying like, oh, well, we should like have somebody come in, take all of our data, and restructure it into things which are a new term then, an old term now, called like a star schema, a snowflake schema, which is basically it's really the idea of like can you resolve a product dimension from your data, a customer dimension, and so on and so forth. And if you could do that, and you could organize it that way, then maybe you could pull all sorts of reports. So that was kind of the theory behind data warehousing, and it worked out fabulously. And so what was kind of relatively fringe in 1995. By 2005 was passé. I mean, by that point, everybody had a data warehouse. I mean, and today, like virtually everybody has a data. Every medium to large company has a data warehouse. And so I started building those. And so early on, I worked for a couple data warehousing consulting companies, and then I decided I want to really learn the skills properly. And so I applied for a job at Oracle in their data warehousing engine building team, which they use this tool called Express, where it was half Oracle database proper, just Oracle, and so that's their relational database, and then they had this multi-dimensional one called Express. And so basically I spent a couple years there learning about that, and while I was there, we're really taking great advantage of of all their certifications. They just started to have this Oracle Certified DBA training, where it was these 4 grueling exams. They actually modeled it on the CPA exams, as far as how difficult it was and what requirements were to get it, and so on and so forth. So they took it really seriously when Oracle first came out with their Oracle Certified DBA or Oracle Certified Professional program. And since I was working at Oracle, then I got all the training for free. So I spent a couple of years really just grinding out about like how exactly do databases work, how do you write queries to do various things. And so then shortly after that, I left Oracle and I went to a startup called Akamai, which is where I am today. But I kind of took a roundabout way of getting back here. So I started at Akamai in 1999. I was there through 2001, and then I flitted off and started my own consulting company. And I worked at a whole bunch of places. I worked at Lenovo, a couple biotechs, some financial companies. And really, and over the next 8 years, what I did slowly evolved. Like first it was, can you build us a data warehouse? Then it was, can you help us figure out what reports we should be pulling from this data warehouse? And so it like slowly blended from more plug and chug data warehousing problems to more management accounting problems about how are we supposed to look at it? How are other companies looking at their data? And so along that time, I'm kind of a nut for certifications, and so I gobbled up ones on certified supply chain professional, and there's this Institute of Management Accountants here in the United States that basically has this management accounting certification. And so I spent a couple years getting that under my belt. That too was actually modeled on the CPA, and then it's 4 exams, all about how can you best represent internal data. So I spent years evolving more from a data warehouse, data architect type of person into more of a management consulting person. And it was funny because it was around then that I had this really interesting thought that I only learned the answer to later. I was actually writing in my blog, and I had this entry about where did all the math go? And I was talking about how here I am writing all these really complicated reports, using best practices to report on data, and yet somehow all I need is sum, min, max, average, count, those 5 functions right there, and that's everything I ever do. I'm like, whatever happened to logarithms and sine waves and differentials and all that other math? And I didn't know at the time. It just seemed maybe that was all kind of a flash in the pan. So what ended up happening is, so in 2009, my dear friend Kate Prouty, who's still here at Akamai, she reached out to me about this plum opportunity to come back to Akamai and lead a project to help them forecast revenue. So specifically, Akamai had a really bad quarter where their revenue forecast had missed by a lot, and so the then chief science officer, now chief executive officer, Tom Layton, basically said he wanted to start a project to have a robot forecast revenue rather than having people do it. And so I came in basically to do that, and that was really, and so 2009, that was when I really first started delving into a lot of hardcore data science. Prior to that, I did do some data science. I mean, for example, I do a lot of stuff with marginal utility curves, and that's when you have multiple options on how basically if you're trying to score the benefit of different things using logarithms to say, basically what logarithms let you do is say that if I have 5 units of something, that's good. But if I have 10 units of it, it's not twice as good. It's better. Maybe 5 units, 5 units of goodness is the same as another marginal 25 units of goodness. So it's kind of saying, oh, you can take off, one day, one day, or you can work from home 1 day a year. That's really good. If you didn't have any days off and you could work 1 day home from a year, that'd be really good. But they say, okay, now you can take off 30 days per year, or you work from 30 days a year. That's good, but it's not the marginal benefit isn't 30 times as great. Sorry, I don't know. But in any case, so I did have a lot of stuff with logarithms, but not really forecasting proper, not really trending and seasonality and a lot of headier forecasting concepts. So that's when I really started delving into it. And so in any case, I built the revenue forecasting model, which is really interesting. I learned a lot about forecasts and how they're used, circumstances, which, by the way, you need to have a person build a forecast. That was one thing that was a real eye-opener for me. So not to jump ahead, but I kind of was of the assumption that if a robot, if an algorithm could generate a better revenue forecast than people could, then you'd use it. I mean, it just seems so obvious. Not so. That's one thing I've learned, that and I've subsequently had this confirmed with other companies. At first glance, you might think that's preposterous. If the computer has a lower error rate forecasting traffic than people do, why would you ever not want to use it? And what it comes down to is that there is this concept of a throat to choke, which is that if you have a company, and let's say there's 10 divisions. By the way, is it okay if I jump ahead? If I jump ahead, sorry, it's just an interesting story.
Yeah.
Okay, thanks. Feel free to repoint me at any moment. But this is really interesting because I spent the first 2 years generating this lovely traffic algorithm, or this traffic forecasting algorithm, and then we use that to forecast revenue. Actually, it probably makes sense for me to step back for a minute and explain what Akamai does and how we forecast revenue here. So Akamai makes websites fast, secure, and reliable. Fast speaks for itself. Secure means can't be hacked from a thousand ways of being hacked, because these days, there's so many ways you can attack a website. Like, for example, you can go after the recursive DNS part of the website, which most people don't even know exists. A few months ago, there was a site called Dyn, D-Y-N, and they handled DNS. Basically, it has to do with kind of like how you point to different servers that have data. So it's not the data, it's not the web content you're delivering itself, but more of a, go to this server to get it. And so that's called domain name server, DNS. And so Amazon used this company called Dyn. Dyn got hacked. And so that's just one of 1,000 ways that companies can hack your sites, is hack your DNS, or there's like distributed denial of service attacks where they don't really hack you so much as just overwhelm you. But in any case, Akamai takes care of all that. So we make sites super fast. So super fast, very secure, and reliable, meaning they never go down. And so the way we make sites fast is that we have a network of now approaching 300,000 servers all over the world. There's 300,000 really high-end servers, SSD drives and lots of RAM, and massive hard drives. And what those servers do is they cache data. So let's say that there's a new Chainsmokers song, and everybody wants it. What will happen is that Apple would give that content to Akamai, and we would distribute that song. So that Chainsmokers song is everywhere. And so when somebody goes to download it, usually they're not even leaving their own zip code. I mean, usually it's like the place they're getting that song from. Like, you might think wow, how many hops does it take for me to get to wherever that song is? And usually it's one, because we have literally that many servers. But of course, what we're storing on all these servers is constantly ebbing and flowing with what is most popular, what's most needed. But the gist is that in the market, Akamai is seen as the premier content delivery network. There are other ones too, like, for example, Amazon. It's telling that Amazon actually hosts their corporate data on Akamai's network, even though they have their own content delivery network. And so it kind of shows that even companies who do content delivery still use Akamai for the tough stuff. And actually, for a while, I don't know if it's still true, but for a while, Akamai had 50 of the top 50 e-commerce sites as its customers, which kind of is telling of how good it is.
I think yes, you guys host 30% of the web traffic, so you better be hosting everyone almost.
Yeah.
Right? So,
oh wow, I'm impressed that you knew that. Yes. We host 30% of the internet traffic, and so in any case, so let me talk about forecasting and like how would you forecast revenue for a company like that? So the way that we make money is it's basically like cell phone plans. Like, picture your cell phone plan where it might be, okay, you'll pay $50 a month, and that will include 100 minutes of talk time, and then if you talk more than 100 minutes, then you'll pay $1 per minute. So picture like a cell phone plan like that. Our plans for our customers are kind of like that. So it's more of a, you can push, you'll pay us $1,000 a month for 50 terabytes. I'm making up numbers here, but something like that. And then if you push more than 50 terabytes, then you'll pay 10 cents per terabyte or whatever, something like that. So the way that when it came to time to forecasting revenue, when I came in, I got this one doozy of a requirement, and that's that the chief science officer said, I want to forecast revenue, but you can't look at historical revenue. And so, which sounded both ridiculous when I first heard it. I was like, why would you not want us to look at historical revenue? And how the heck are we supposed to do it if we can't look at historical revenue? And he's like, he had good reasons for both, or good reasons for the first, at least. And he's like, well, the problem is that sometimes our revenue's gone up the past 4 quarters, and our markets are volatile. And when revenue's gone up the past 4 quarters, it's almost impossible, no matter how you write an algorithm that's going to forecast revenue based on revenue, it's going to say you're going to keep going up, because and so he's like, so therefore, I need some other way to predict revenue other than just looking in the past, because you'll tell me a lovely revenue forecast, and it will be wrong. Whenever there's like a jolt in the market, it'll be wrong.
No, I think
so
one thing that I really like about this sort of fascinating request, and even like in our conversation, we talked to a lot of executives who are sort of planning their way ahead, and this is, I think, one of the very groundbreaking thought, right? So that let's look forward, because I think many times you just say, okay, the system is causal, so we'll look back, we'll take this into account, and then create a model that goes forward. And I think the very fact that Tom has that much of vision of, okay, let's just stand here and just look forward and not look back in your analysis, I think that puts a lot of pressure on you to be a lot more creative and sort of letting all this intuition on, like, I think as much intuitive capabilities in the model as I think that's fascinating. I think that's a very, very, very not many story I've heard. I think that's why I'm fascinated by this story for sure.
Oh, these, yeah. It kind of reminds me of there's an expression: all generals are preparing to win the last war. Have you heard that?
Yes.
They're always saying, like, what just happened? Okay, like I'll prepare to win that, and then you get sucker punched again and again and again, because of course the next war is never like the last war. And so this is kind of like that. And so he told me that, and then I had to go off and think about it. I'm like, okay, how the heck am I going to forecast revenue without looking at revenue? And I came up with an idea. I said, like, well, our customers have billable traffic, and they push that every month, and we have contracts with our customers, which can be actually extremely complicated, but nevertheless, we have them. I said, what if we forecast internet traffic patterns, forecast the billable traffic for every one of our customers. And once we have those traffic numbers, then run it through the invoicing system based on the current contracts. And so what one person told me before, and it's always kind of stuck with me, they said, like, well, that's not really a forecast, that's kind of a simulation. And that, like, and I've always, like, that kind of stuck in my brain, where, like, to this day I'm like, what is the difference between a simulation and a forecast? Right. And, like, I don't know where I would draw the line, but I was like, yeah, I guess if you think of it that way, I guess it's kind of it's a simulation. And so that's what we did. And so we ended up obsessing. We spent like a year and a half. I had the benefit of working closely with Tom, where, ironically, even though our whole goal was to forecast revenue, we spent all that time trying to figure out how to forecast internet traffic patterns. And that, we found out, was really, really hard.
Right.
And it's just funny. Like, can I jump into talking about forecasting traffic and like, and how it's funny. Like, when people think of forecasting, their expectations are greatly set by the few forecasts that they know about, and most people only know about two. Well, there's two that come to mind over and over and over. One is weather. And it's just kind of like everybody has a weather forecast, and everybody is, like, wants to be first in line to say that the weatherman stinks. Everybody loves to say how much the weatherman stinks. The second is the presidential elections. They know those forecasts too. And I think actually both of those can shed great light on like what you're up against with a forecast. So let's talk first about the difference between forecasting traffic for customers versus, say, forecasting the election. So if you're forecasting the election, that's actually really easy in comparison. Nothing is easy in absolute terms, but in relative terms, crazy easy. And for two reasons. One is, in general, there's only really two options for any one person. I mean, three if you want to get all fancy about it. It's like you voted for Trump, or you voted for Hillary Clinton, or I guess you voted for a third-party candidate. But so there's like an extremely limited number of options, and every person only votes once. And as a result, your highs and your lows greatly cancel out. And that actually, there's a name for that. That's called the central limit theorem.
Right.
So central limit theorem is. Yep. Okay, yeah. So that we'll just that's why, like, if I flip a coin once and I ask you what it is, you'll be like, I don't know. It could be heads or tails. But if I flipped it 1,000 times, like, you could take to the bank that you're going to get about half and half. Like, you don't know what any one flip will do, but you'd be shocked if you had 1,000 flips if they were all heads. That would be weird. And so so when it comes to the presidential election, your highs and lows cancel out, and as a result, that's why they can say things like within 3% confidence we think the poll will work. Where the they'll interview 120 people and they exit the polls, and then they come up with this 3% confidence, and all these statisticians all nod their heads, and you're pretty sure they're all really smart. So you kind of think like, okay, I guess they know what they're doing. So now compare that to forecasting traffic for an individual customer. So first off, highs and lows don't really cancel out anymore, because it's just one customer at a time. That was the other thing that I should have mentioned, is that like our goal was to get a very accurate individual forecasts, and then with the hope that then those would all add up. And well, in any case, so yeah, originally we were just looking at traffic. We're like, okay, how do we forecast each individual customer? And we found it was really hard. It's really hard because first off, like, it's not an on or off. It's not will the customer have traffic this month or not. It can spike greatly. Like if you're looking at, for example, like Victoria's Secret, that was one of our customers. If you looked at their traffic in say August, they're not doing much of anything. If you look in December, it's through the roof.
Right.
So a lot of customers are like ferociously seasonal, and on top of that, are constantly like rolling out like new revisions of their software, launching new sites, consolidating or splitting apart traffic. And so if you look at the past of any one of our customers, it's really, really hard to forecast it. And the need to mitigate noise is because basically there's just all this random volatility, and you try to like look through that and then sift out like, okay, what is the true effect of seasonality versus what's just noise? But in any case, so I had the benefit of spending a year and a half to just come up with a really solid traffic forecast. And then once we had that, we fed it through the invoicing system, and for those of people watching this who are vaguely aware of accounting, invoicing and revenue are usually joined at the hip. So usually the only difference between when you invoice a customer for $1,000 and when you recognize that $1,000 as revenue is usually just a matter of timing.
Right.
And to make a long story short, that wasn't that big of a deal. So like if we could get the invoices right, our revenue was pretty good. So let me jump to the I guess I already talked about this concept of throat to choke, and like what. So we came up with this great revenue forecast, and then the CFO was like, I don't want to use it. I would love it as a triangulation point, but I can't use it to run the company. And I was like shocked. I'm like why would you not? Very good reasons, and that's because if you have like 10 groups and 10 business units in your company, and you want to you're trying to figure out how much money we're going to make in aggregate. So you ask all 10 of them, okay, for your section of the company, how much money are you going to make? So they give a number, and then you add them up, and that's the forecast.
Right.
So now when you do it that way, each one of those people feels a strong sense of responsibility to nail their part, to get it right. And so now they're sweating it all quarter to make sure that they hit the number that they got. And also, if at the end of the quarter they missed, then the CFO can go back and say, hey, you're in trouble now because you said X and you didn't deliver X. So now compare that to an automated forecast. If there's an automated forecast, then those people are totally off the hook. They're not in charge of anything. So they have no compunction to hit the number because they didn't even give the number.
Interesting.
And so and if anything, there's a great incentive just to grouse about the number. No matter what the number is, it's easy for them to say like, oh, that's way too high. Like you're being too ambitious, because there's no benefit for them to say, oh, that number's too low. There's great benefit for them to say it's too high. But anyway, to make a long story short, like a lot of times, like what is true from a mathematical sense, and I think that you and I have talked about this before about how like data science often kind of exists at the intersection of what makes sense mathematically versus what makes sense operationally.
Right.
Because sometimes things like mathematically, of course you'd want to do it a certain way. Operationally, not so. Can't do it, won't work.
No, I think one thing definitely that I do appreciate here is and I think we talked about it, the art of doing business and science of doing business. And I think the very fact that you made your model account for hey, it's, my forecast is not really mathematical, but it has operational. It's accommodating operational hiccup as well. I think that makes it very robust, right? Because now it's the model itself is very human in itself, right? So it can accommodate. It's not putting too much pressure on the sales guys. It's saying, okay, whatever you go and do, and that's what we understand, and we appreciate that. I think that's fascinating, by the way.
Well, it's funny. So you touch upon an interesting point about making a model human.
Right.
I'm convinced that terminology is going to become that you're going to hear more of that, and the reason is that it's funny. Like I often give this. I work with a lot of data scientists, and I see like how they've been trained, and I feel like I have to kind of like untrain the data scientists that work with sometimes on like bad habits, and so let me describe like how I perceive them being trained,
right?
And what's wrong with that. So it seems like the way the schools train data modelers is they say, okay, here's some data, find the model that best predicts, basically best predicts whatever you're trying to predict, and throw as much math at it as you can. And so, they have these really heady models in Python and R, using, with the random forests or, all sorts of time series, Box Jenkins. I mean, I'm familiar with all the models. I mean,
right.
Or I certainly know a lot of them. And so they throw all this math at it to try to come up with the best answer, and they are graded based on how well they do. Now, I do think that in some areas of business that works, but mostly it doesn't work at all.
Right.
And that actually, and this might sound perverse, that accuracy is actually not the most important thing, which sounds crazy. So here, but let me explain such a crazy statement. Okay. What I mean by that is accuracy given your assumptions is not the height of
that's true
of it, because so consider this. Consider if let me take a step back. Yeah, so here's how a lot of data scientists kind of thought the world was going to work. Is they would be given a problem, they would collect some data, make the best mathematical forecast they can with that data set, come up with something that is mathematically spectacular, and then everybody would love it, and they would all use it, and they would win awards and stuff like that, and that would be the end of that.
Right.
That's not how it plays out. It was funny. I think partly because I came up from a different perspective. I came up from the perspective of building progressively more sophisticated reports, rather than and the forecasting was secondary, rather than saying oh well, it's all about the model, and then the reporting is secondary.
Right.
So let me give you a real life example of how people think it plays out versus how it does. And so imagine if somebody asked me to make a model to determine which kids in a school should qualify for special education. Okay. So I looked through it, and I realized that there's resource constraints of how many kids could we even afford to put in special education, and how many kids are there, and what are the different ways you could evaluate a kid. So I come up with a model. I'm like, okay, this is my best model, and let's say it uses some really heady math. Let's say that I don't even really know how it works.
Right.
I just know that I just put it in, and it just said here are the coefficients and that best predict blah blah blah, and I'll use that. Okay, so I've got my model. Now I'm going to sit down with a parent, and that parent, and I just basically, I have to convey to that parent oh yeah, your child's not going to qualify for special education this year, and that parent seriously thinks that they should.
Right.
They're going to want to know how the model works. They're not going to say, oh, does it use a lot of math? Oh, okay, as long as it uses graph theory, then I'm sure it's way smarter than I am. So one is they're going to want to know. Two is they will know more information about their child than you did when you made the model.
I think that's a very interesting point. Yes.
It is, and it's funny because so they'll know all sorts of stuff that that you couldn't have practically put it in the model because you couldn't have collected that information about all the kids.
I think so.
However,
I think you have a very interesting point here. So pardon me, I'm just jumping in the middle quickly because I think so. Yesterday I went to this charity and I met this professor from mathematics, and I was having this interesting discussion with him, and it got into a very interesting sort of side. So the thought is, and you would appreciate that. So when math was designed initially, right? Mathematics was humans' way to visualize something. There was no monitors, there was no, so every mathematical model just tries to draw a circle or a line and then say, okay, if I'm going to moon, how would that look like, and how would the trajectory, what all other sort of wind, and these are all like lines and circles and spheres that we're trying to explain the phenomena, right? But now when we have so much sophisticated visualization models and so much sophistication sort of computer algorithms and computer systems, many times, like I think, and you are bringing up some of the interesting point that, like, it's not heavy with math, right? Because the math itself is not designed to exist in today's scenario, the traditional typical maths, right? And I was discussing with him that we have to, even from a mathematical point of view, redesign the entire paradigm, because now there's something called, I think, error bars, right? So at certain values, many of the equations start to falter. The error increases beyond the permissible limits, and sort of it just cracks down. And it's very sort of, and I think one thing that you are very interestingly raising a point, which I would even let my audience to sort of think through, would be that many times data scientists, we try to bring in maths, very typical traditional hardcore maths to prove a model, but that when that particular model was designed, I think that's another area, and I think you are actually hitting it right at the ballpark, that the parent know about that kid more than you do, or your math does, right? So you are constraining that prediction or that sort of that selection criteria on your limited visibility on the situation, and not really accommodating the localized scenario of each kid, of what they're going through and who would sort of get the better care. So I think that's a very interesting point, and most of the interesting or successful model, that's why have intuition in it as well. That's why they want to capture some guys thinking, okay, maybe it's not making sense on a model sense, but I have a nice hunch maybe, and that has some role to play in the model as well. So I'm sorry, that thought immediately came in the middle, so I thought I'll just push it out pretty quickly.
Oh, yeah. Well, and I think what it comes down to, like, the idea of making a model human is that if you can have your model be fully explainable, where the other person knows exactly what you looked at and what you didn't, and how you reached your conclusions, then when the person using your model has extra information, they can complement it. Right. And so I'll give you a perfect example of this. Let's say that I make a traffic forecast, or revenue forecast for a given customer, and that finds its hands into or finds its way into the hands of the sales rep for that customer. Okay, and let's say that the rep is really trying to figure out, like, well, how much is this customer going to make? And so I'm saying, like, oh, they'll make us $100,000 over the next 3 months. Now that rep might say, like, well, shoot, like, the next 3 months are November, December, January. Those are 3 really big months for this customer. Did he factor that into the model already? Because if he didn't, then I want to add that in. And maybe I did factor it in, and maybe I didn't factor it in. Or maybe he'll say, like, a month and a half from now, the customer's switching over from one product to another, and when they do, they're gonna push more traffic on our network. Again, did Brett factor that in, or did he not factor it in? Now, if I just say, I've got a model and it uses coefficients and it uses high math and it says this, that's all I can tell you. Now I'm putting that rep in a really crappy position where, like, he can either use my model and totally kind of submit to whatever high math is doing, or he could throw it in the trash and make his own model. Like, those are the only 2 options. Like, there's no way for him to complement mine with what he has. And so what I've tried to do here at Akamai is, like, when we make models, is say, here's exactly how I did it. And it's funny, even things awesome. Like people say, like, hey, I see that you are predicting that they're going to push a lot of traffic in December. Why are you saying that? Because last December they didn't push much at all. And I'm at the point where I can say, like, oh, well, it's true. Last December they didn't, but the 3 Decembers before that they did. And so therefore, last December was considered an outlier, and kind of like conveying that to them. But then also, saying, like, but hey, like, if you know better, like, and you will know better, like, because there's this problem in any model of locality. Is that, like, when you're making the model, little bit kind of pie in the sky. Like you don't know the local situation. Like you're just dealing in generalities.
No, I think.
But then when they actually have to use it.
And I think one thing that I really like from our last meeting, that you actually let your sales folks play with it. I think that's the fascinating thing about your sort of your algorithms, right? You would let these guys define the values and see what's going on. I think that's pretty cool.
Oh, sure.
Yeah, so I think that's to sort of to get their intuition into your model. I think that's fascinating as well.
Well, it's funny is I have this one kind of amusing anecdote about like data science is like food science. Okay, or like food science was 50 years ago. In that, consider Wonder Bread for a moment. Okay, and imagine if you've been a parent who says like, oh yeah, I feed my kid Wonder Bread all the time. That's all I feed them, Wonder Bread. Like you probably would not view them as prestigiously as if they fed their kid whole grain bread. Because Wonder Bread is usually considered like kind of crap bread.
Right.
But the thing that people often forget is that like when they originally made Wonder Bread, they literally thought Wonder Bread, bread of the gods, like the bread that we'll all eat. Because why would you ever eat that junk when you can eat Wonder Bread? Which sounds like it makes me giggle just thinking about it. But that's what they thought. And if you were to say like, why would you have thought that? Like, why would you think we would all eat Wonder Bread like at the time? And they're like, oh, because we have food scientists. Like Wonder Bread is made with food scientists. We have additives and preservatives. And this is back before the term additive and preservative had kind of like a negative connotation. Back then, like those were like, that's like science laid bare. Like, oh my God, like it's like bread, it's bread plus plus. It's like bread plus better in every way because there's some guy in a lab coat, with a vial pouring it into the mix. And like that's not how we see it now. Now if anything, we're like, I want to know exactly how it was made. And like if you have some like hyper complicated way to make a slice of bread, that's a bad thing, not a good thing.
That's true.
And it's kind of like that with models too. Is that like people want models, like they want models that are simple and understandable. Now I do realize that probably right now a lot of people would get upset that I just said simple, because it's like, well, hey, like if you stuck to simple stuff, you won't get good results, and that is totally true. Yeah. I mean, like sometimes you need to do advanced math. Right. You need to use eigenvalues, for example, or for that matter, even logarithms or sine waves, in order to properly predict stuff. However, I think that the proper perspective that you should have as a data scientist doing those things is that they're necessary evils. Right. So there's a necessary evil that I have to do this math, but it doubles the burden on me. It's funny, like usually the way most data scientists think about that, if they have to use advanced math, they see that as a win. They see that as like a hooray for me because I'm so smart, and it shows how smart I am that I can use eigenvalues here, and it reinforces the value that I'm adding. That is not the right way to look at it.
And I think
a better way to look.
I think that's what I like when I was looking at your profile. I think that's what, because when you come from the data science world or data scientist world, I think math precedes, or at least the science precedes the art, and I think that's why you're coming from the art world, saying okay, and that's why I think I want to humanize this, and that's why I think one thing that was very fascinating to me, which I want users to take away from this conversation, was how open you are in capturing the feedbacks and thoughts into your model, and how open you are in communicating your model's complexity in a very simplistic way, so people can understand and they can pitch in and they can contribute. And I think that's if you have that mix, that's toxic. Like that's beautiful. That gets something that is workable. I think that from that point of view, I think that you're doing a great job there for sure.
Oh, I'm glad you think so. And I should mention that, I bet a lot of people right now are thinking, like, yeah, but I bet his models are all terrible. Because if you limit yourself to simplicity, and that's the thing is, I don't limit myself to simplicity. It's just that, like, when I have to do complicated things, I realize that there's a burden upon me to be able to explain simply to people so they can understand how it works. And it's funny because like even those basic things, like when I interview people, like there's like here's an example of of the type of question that like I'll ask in an interview. I'll say like explain what a geometric average is and why you would ever want to use it, and how is it different from an arithmetic average. And a lot of data scientists, like, they know geometric averages backwards and forwards, but when they have to put it into plain English, they kind of fall apart.
Yeah,
they can say like, oh, well, that's for dependent variables. I'm like, okay, what's a dependent variable? And then like, and it's like, and I would have to like remind them, say like, look, if you can't, if you're using geometric averages in your code, or in your model, then people are going to ask like, how did you combine these numbers to get that average? Because that's not what I got when I did it.
Right.
And you say like, oh, because you're doing an arithmetic average, and this is a geometric average, and this,
so I think,
and this implies dependency. Yeah?
Yes, so I think that's rightly so. So tell me, I think so. One thing I definitely want to capture in the conversation as well. So I was researching your profile, and I think I read something about forecast with 5 averages. I definitely want your attention in what the hell is that, and it reads beautiful. It made sense. So why don't you share with our audience what is forecast with 5 averages?
Oh, sure. Yeah. Well, it's funny because like the 5 averages to me, it's kind of like martial arts, where like when people think about martial arts, usually their brains go to hurricane kicks and nunchucks and like really like exotic, flashy stuff. But if you were to like talk to to a true martial artist, like they would say like, well, you really get 90% of the value if you just learn how to throw a good punch. If you just know how to throw like a really solid punch, like then you're way ahead of the game. Like the hurricane kicks, like you don't actually do a lot of hurricane kicks in real life. And if you're trying to, then you're probably working too hard. Well, it's kind of like that with forecasting, and then like a lot of forecasting is like a forecast in a lot of ways is really an average. It's some application of averages. And one thing that I discovered earlier in my career is that like there's actually more than one way to take an average. There's 5. And understanding like when would you want to use each? Because I've used all them all each all the time. So, and it's funny, like most people know the first 3, which is mean, median, mode. Poor mode. Everybody makes fun of mode. Like I don't know if you recall, like mode just means like the value that comes up the most often.
Right.
And so if I ask you for your quote like average, or if I said like, what do you think is the average favorite flavor of ice cream? You're like, average ice cream? I can't do that. It's like, no, but you can. It's probably vanilla, or I don't know, maybe chocolate chip cookie dough if my kids have any say in the matter. But basically it's just the value that comes up most often. And so that's a form of an average. And in fact, like it's like, where would we be without it? Because basically mode is how people use to set defaults. Like whenever you have any application, that's like one thing that like in a lot of the models I'll build, I'll say like whenever you set any when I give a model and there's like 10 different inputs, whenever somebody sets one, anything they haven't specified, I will set those to the mode of the remaining values. Say, okay, well, you probably wanted these values, and so they're like, which like really helps to guide them. So, but in any case, yeah. So mode is just the value that happens most often. Median versus mean is really important because mean, of course, is just your average. I mean, that's just your classic. What grade am I getting in this class? Average. Add them up, divide by the number, done. Whereas median, of course, is the middle, and that can be really important, especially with crazy data, because if you want to keep the outliers from skewing your data, so then you use median. So usually people know those 3, but then the other 2 is a geometric average, also known as CAGR. It's funny, like finance people know as CAGR, which is a compound average growth rate, or geometric average. That's why it is that if you have a stock, this is funny. This is something that like for years puzzled me. I'm embarrassed to admit it, but maybe about 10 years ago I was like, oh, that's why I'm wrong. But like if you have a stock and it went up 10% in one year and then it went down by 10% the next year, somehow you're not back to where you started. I was always like, why am I not? I don't get like, why can't I do this math? Because like it seems to me that, and of course it's because they're compounding.
Right.
In other words, last year's value is based on, or this year's value is based on last year's value. So that's what they call dependent variables. And it was funny because early on, when I was doing traffic forecasts, it was this intricate mix of geometric and arithmetic, because if you're saying like, well, what is the average growth rate of these 5 companies, then within any one month, well, that's an arithmetic. But if you said, like, what is the average growth rate of this company over the past 5 months, that's geometric, because like the past 5 months growth, how much they grew in October affects November.
Right.
But if you're just looking for, like, so anyway, so there's that, and then last but not least, there's one called harmonic,
Right.
the harmonic average, and that's for rates. And so that's the whole. You remember back in, like, when you studied algebra, when they give you problems like, if you have one machine that can produce a unit every 5 minutes and another machine that can produce a unit every 9 minutes, and then now you have both of those machines, how often can you produce a unit? And like doing those math problems. So basically, like, if you're using rates, then use something called the harmonic average. And just like, I feel like for any data scientists, it should really start with that. Is like really mastering like what are the different averages? When do you use each one? Because like if you just know that, you could do a lot. Like that's your solid punches. Like knowing that, and then as opposed to your Box Jenkins, which is like your hurricane kick, because that's Box Jenkins is this more advanced time series algorithm. I believe it's time series algorithm. But like, which is really exotic and impressive as hell if you can find a way to pull it off.
Right.
But more often than not, you're just going to confuse everybody, and it maybe doesn't even apply to your circumstances.
So I think well said, by the way. So now I'll go slightly back on the time when. So Tom said, "Okay, get me this model, build me this something that is forward-looking, future-looking, right?" So what is that first thing that comes to you during that? So if suppose you need to put something in a very constrained environment and whatever, right? So what was you thinking then, and what were like a couple of steps that you took to get started? And if you can share such that will be helpful.
A great question. Yeah, and actually I think that so I kind of have this like secret of like how I build all my models, which might be kind of ghetto. I don't know if that's the right word, or like kind of sketchy. But like whenever I'm trying to build a model, then I always do it the same way, where I think like, okay, well, how would an extremely bright person go about this? And I would do it that way. In other words, like, I don't have to solve the problem.
Right.
Just figure out what somebody else would do and then automate it. If you can. I mean, like, you can't always do that. And actually, which is really interesting. I could talk about how, like, one term that, I'll talk about that, but I would like to get back to like, people have this idea that common sense is like easy. No. Common sense is like, I will never build a model that has common sense. Like because common sense is as a standard, and I can tell you why. Like, I mean, I can give you examples. Common sense as a standard is like if I could ever build a model that like approached human level common sense, like, I would be done. I should win every award known to man. And I can give examples of like why it is that people think common sense is so simple. But to get first to like, how did I go about building the model? So this is what I thought. I thought like, okay, well, how would a person know? When I was trying to forecast traffic forecast revenue for our customers, first thing I did was say, like, well, how would a sales rep know? Like, how would a sales rep, like somebody really close to the situation, or how would the customer themselves know if they were going to pay a lot or a little? Like, I mean, because you figure, like, who would know best? Well, probably the customer themselves is going to have a good understanding. So that'd be like, if I wanted to know, how many minutes or how much Vishal is going to pay for his cell phone, like, who better to ask than you,
Right.
and because you're close to the situation. And so then I quickly was like, how, and so then I was like, okay, how would they know? Well, they, much like you, would say, like, how much usage am I doing? Am I talking a lot this month? No? Okay, well, then I don't think I'm going to pay that much. Am I talking a ton of minutes? Okay, I'm going to probably pay a lot. And so that was kind of my first idea, was to say, like, okay, how would a customer know? Oh, well, they would know based on their traffic. And then I'm like, oh, okay, so if I could basically just figure out the traffic and then run that through the invoicing system. Oh, that's another thing, by the way, is that like I say running it through the invoicing system like that's easy. Like, you can just make a forecast and run it through the invoicing system. Like, I do think that, like, one benefit that I had over a lot of, say, proper data scientists is mastery of SQL, and the ability to, like, transform data into just whatever format you need to get the job done. Because in this case, like, making the forecast traffic forecast was one thing. Feeding it through the invoicing system in all the formats it needed in was quite another, and like, so being able to do that was tricky. But I'm sorry, I got off course. To answer your question, like, how did I go about it? So what I always say is like, well, how would an expert do this? How would an expert know, like how much money we're going to make? And then and kind of cheat, because like that's the thing is like people in general have very clever ways of figuring things out. Like quite often, if you could just automate what a person would do naturally, there's actually a double bonus to that.
That's beautiful.
One is it's probably so the first bonus, benefit is that it's probably a pretty good way to do it. Okay, so you can say like, okay, how would just a super bright person who had to do this manually? What would they do? Okay, I'm going to automate that. So that's the first one. The second one, and this is is huge value, is I guess actually the three, is that it's very human. Like when you do it that way, and then you explain to people what you did, then it's very pleasing to them. Because they say, oh, that's what I would have done, as opposed to if you just like throw a bunch of math in their face where they're like, dude, like, I don't even know what you're talking about, like, so it's very human. But also when you do it the way they would do it, more often than not, it lets them complement your forecast with other information. So when I say to the rep, like, well, what I'm doing is figuring out what their traffic is based on what they've done in the past, and then I run it through the invoicing system. So now let's say that the rep says like, oh, I know that they're changing contracts next month. Would that have affected what Brett, what Brett forecast? And more often than not, like they can figure out like, oh yeah, that would totally affect the forecast. So I can't trust what Brett's going to give me because this is changing one of his base assumptions.
Right.
Or saying like, no, he's probably got that under control. Or finally saying like, okay, I just need to bump up what Brett said a little bit. Like they can do things like that. Whereas if I just said, I put it into the crazy supercomputer and it spit out this number, like then they're helpless. Then there's nothing.
No, I think
but I'd like to get back
makes sense. Yeah. Sorry. Yes.
I'd like to get back to common sense for a moment, and like why it is that like everybody loves to deride common sense. So can I expound upon like why getting common sense is so hard? Or because I think people miss this. They think common sense is just like is basic. In other words, they're like, well, common sense would never take the sine wave or derivative of something, and that's I guess more or less true. But what common sense has, which is so incredibly valuable, is dynamic materiality. And so I give you the example of this. Okay? So imagine if you said, Brett, make an algorithm that's going to predict whether I will find a certain person attractive as a mate. In other words, like something that's going to predict which women I should ask out on a date, or something like that. Okay, and so I make my model. So now consider this. I'll give you some people that it could have considered. The first woman, spent time in jail. Second woman has terminal cancer. The third one, lives with her parents. Like, would I have known to factor those things in? These kind of like low probability events. So it's like low probability, but they matter if you know them.
Impact,
let's measure. And that's the thing is like if I were to say with a girl, and she had terminal cancer, you might be like, Brett, like don't set me up with a girl if she's had terminal cancer. Sorry, I realize that's politically crazy correct. I shouldn't. But like in other words, it could be something that's like egregiously bad, but very very uncommon, and they're like where people know it on site. Or if I say with a girl who was like a billionaire. Like that's very relevant, as opposed to if I set you up with a girl who tends to take back roads to get to work rather than the highway, that is not very relevant. Models don't usually like what it really comes down to is that to really nail common sense, you would have to handle thousands and thousands of these like little edge cases that are all obvious once you know to look for them. But you just have to know to look for them, and like so common sense knows those things. Where like my model would never predict those things. It's not going to.
No, I think so. You are actually raising one very interesting point, and I could like to quickly jump in. So one thing that I use a lot. I read a lot, and I read a lot of history. So I think many of the business problems are either like I find a solution either in some war scenario with some general and how they attack. And so the idea is that if, like, I'm looking for the intuition, right? So in that scenario, what was the intuition saying for someone who is actually doing this thing again and again? Whether it's a finding where to invade next, whether you figure out if you have less workforce and you are battling with the army of those like big armies, how would you do that? Or whether you say a typical natural evolution. I think you have a brilliant point of finding a parallel story, and sort of and from that take the inspiration into your model, and if, because there it works, and you have seen it works, so there's a strong confidence that probably if in your case it would translate to some success as well. If not, like it won't be catastrophic failure at the least. So I think that's a beautiful point that you said, that having sort of some parallel to sort of map it, and that's how you envisioned when you just jumped on that problem. That was very helpful.
Oh, sure, yeah. But you're right. I mean, reading about how other people have done it, is powerful. But especially that's the thing is, like, when it comes to algorithms on how to forecast things, I do think that a lot of data scientists pay little respect to how people do it now, and because there's kind of this distaste for I'm going to apply such advanced math, I don't even care how they do it now, without saying what if I took exactly how they do it now and just try to make it, one, fully automated, and two, spot the flaws in what they're doing now and improve them. You might find that there's that when you start from scratch every time, and that it's kind of throwing the baby out with the bathwater. That a lot of times there can be real insights into how people are already applying data science. They're just not calling it data science, but people are already today forecasting deals, valuing things, prioritizing, stack ranking. They're doing all these things. Right. And somehow the world goes on, and some people are more successful than others. And so paying a closer attention of the respect for how they do it, and then saying oh, maybe I should just automate what they do today. And and what I found is
that's well said. So I think one thing that definitely I want your perspective on is, so who is your ideal hire? So if you want to hire someone, who is your darling hire when it comes to sort of
sure, yeah. Well, it's tricky. There's one other area we haven't spoken about, because that's technical skills. So as far as what technical skills would you want? And here I am definitely against the mainstream right now. The mainstream right now says, it's all about R and Python. R and Python, those are the best. Everybody uses R and Python. Most of my models I build in SQL. And you can do amazing things in SQL. The problem is that most data scientists are just trained SQL. That's just the thing that gives me my data. Right. That's just that's like the data butler, but you can't actually do anything in SQL. No, you can do amazing things in SQL. In fact, case in point, at Akamai, that traffic forecasting algorithm that I was telling you about before, I built that in SQL. I mean, it's some pretty heady SQL logic. But then after the fact, a few years later, 5 years later, so I built that in 2009, 2010. So in 2013, IT hired 2 data scientists, and they used Python and R, and they came in to rebuild it. The idea that they couldn't do better was not on the table. I mean, they're well, of course we're going to do better, and basically from their perspective, it seemed it's almost like they saw that I built a skyscraper out of wood. They're wow, you built this amazing engine in SQL? You're not supposed to use SQL for that. You're supposed to use R and Python. It's kind of like them saying, we have steel for your tall buildings, Brett. You shouldn't really be building them out of wood. And so they spent a year on it, and they said, just keep it. It's better the way it is now. So generally what they said, well, we can make it better. That's data scientists are never going to tell you they can't make it better. They said right. We can make it better, but it won't be materially better, and nobody will understand what it does. So just keep what you have now. But it's funny because actually, one thing that I've really been honing my skills on is solving mathematical problems using SQL, like taking all these like advanced algebraic and just either algebraic or calculus problems, and then say like, can I write a SQL statement to do that? Like here, case in point, like there was one I just solved yesterday in SQL. But me and my friend Vinod with this book, this is right here, this Shakuntala Devi. This is like this famous Indian woman.
I'm a big
she writes
fan.
about.
Yes, I think almost every Indian is a fan of Shakuntala Devi. Yes.
Oh, I didn't know that. Wow.
She's brilliant.
So like, she really is. And so like we take her problems and we try to solve them using nothing but SQL. And so like, I'll just to give you a flavor of like, this is a problem we just solved yesterday in SQL, and it took us about a minute and a half. And like, I freaking dare people in R and Python, like, can you even do that in a minute and a half? And then by a minute and a half, I don't mean that's how long it ran. I mean like that's how long it took us to write the program. And so here it is. It said, consider the set of numbers from consider the set of 9-digit numbers that contain one of each non-zero digit. So therefore, the number 1, 2, 3, 4, 5, 6, 7, 8, 9 to 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so like the combination between those, all the combinations of those 9 digits. What is the largest and the smallest number that has an integer square root? And which is kind of tricky. Like, like how would you even do that? And so like here, I'll send you the code. And so if you have like on the just in case people are like, bullshit, you can't do that in SQL. Like
I would agree with those guys. So
no, you can do SQL. SQL. It's funny. Like SQL is set theory. And set theory is ferociously powerful. It's all about like aggregating and comparing individuals to sets and combinations. And yes, I'll send you the actual code.
That will be awesome. I think I'll paste it out for users to see. So, Brett, I think that brings us to almost the end of the conversation.
Oh yeah.
So one thing, definitely I want to hear from you before we part. What is your suggestion for new and emerging leader who is just got into the situation of design something for me or my companies, put a data science team together or design it or make me smart through data? Like what are some of the suggestions that you give to this mythical magical guy who's jumping on this role of leading a group of data science professionals to deliver data-driven intelligence? So what are some of the thoughts?
Okay, so first one is, and the most important, don't fall in love with the math. So many people fall in love with math, and they fall in love with like, oh, graph theory. I love graph theory. It's amazing in so many ways. And before they know it, they're just trying to find a solution for this lovely math that they have, not realizing that that's just suboptimal. It's not good, So like fall in love with helping people do better work. If you really think about information theory and like, well, what is the value of information? And I think at this point, like, it's common knowledge that the value of information is measured in the marginal improvement in the decisions that are made using it. So if you have like math and it's like really impressive math, but it doesn't really help anybody make decisions, or maybe it would, but nobody's using it because because they don't really know how it works, they're all spooked by it. Then that has very low value. Whereas you do something that is like really lame or seems lame, but it really helps. And maybe just taking like a weighted average of something. I don't know. I mean, but just if you're in some situation where you're like, oh, it's really not that much to it, but it's definitely substantially better than they're doing now.
Right.
That has great value. Now this is a point of great dissonance. It's almost painful for data scientists to hear. They don't want to hear that like the advanced math isn't where all the value is, And I'm not saying that there's not value in advanced math sometimes, but I am saying that like the more heady the math in general, it hurts more than helps, because like you'll make it 5% better and nobody will know what the hell you're doing, including the guy who takes over your model when you leave the company, and so
that's true.
So maybe the first thing is like it's funny. There's this line in the Tao Te Ching, which says, and this is slightly dated line, but it says like, know the masculine but stick to the feminine. And I would say, like, and I think what he was trying to say, and in his 4,000-year-old line, is like, know how to be tough, but try to be nice,
flexible, right?
And I feel when it comes to data science, it's like, know how to do the heavy math, but try not to, because like it hurts more than it helps. Like throwing intimidating equations at every problem is not the answer any more than like fist fighting every person you meet is, because it's just and so I would say that is yes. One is don't fall in love with the math. Second is hone your mathematical skills. It's important, but also hone your explanation skills, because your explanation skills will matter just as much. The ability to articulate exactly what you're doing, why you're doing it. I'm not saying that I'm necessarily the best in the world, but if you can work on both writing and verbal to to explain things, because you're going to need to, because this idea people have that all people bow at the altar of high mathematics, and that if you make this like fancy dancy algorithm that everybody's just going to use it, is false. Like, you're going to have to persuade people on why they can trust it. And why they're better off using it, and a lot of that's going to have they're going to have questions like, well, why does it say what it says? And that's an explanation problem, And so so I'd say like those would be the two biggest things. One is don't fall in love with the math, and learn hone your explanation skills as much as you hone your mathematical skills, because ultimately
that's beautifully said, and I think I love it, and to our audience, I would like to say that. So I had a bunch of interesting questions planned for Brett, and I think you are so fascinating. Like I'm barely half in my list, so probably I'll pull you in for a second round. I think we learned a lot. I think one of the takeaway that I think from your conversation is again, humanize your math. I think I think that's remarkable, right? For sure, right? And then your insights on don't be fancy dancy on using math. Just be flexible, be communicative, and get other people's input in your model. I think those are some of the exceptionally fascinating thoughts that even we are seeing from some of the exceptional leaders doing, who are actually rolling out the practice in a very successful way. So I think that's a great takeaway for our audience. And Brett, again, thank you so much for being so much generous with your time and walking us through your journey, being very candid about it, and sharing your journey through how you worked on that model, and pretty much walking us through the process of what it takes to deliver a fascinating forecasting algorithm. I think thank you so much, and love to have you again, as I said, for the part 2 and ever again to learn from you and to share your wisdom with our audience.
Oh, it's been my pleasure. So thank you so much, Vishal.
I thought I was sick of home, but actually I was homesick. Never really knew that I would have to grow up so quick. I'm so uncomfortable, don't know anybody here. Just a couple dudes that I met once, that's it. And I go into the booth feeling nervous. Got butterflies in my stomach like I'm so worthless. Is the mic on? I don't know how to work this. Inside I'm breaking down, I hope I'm not up on the